Screen. Yep.
Thank you.
You're audible.
Okay, hello, may I start? Hello, everyone. I'm Kido Tani at Ibaraki University. Today, I'm talking about a temporal sound-based controlling device. IoT devices are widely used for controlling home appliances via internet. Remote controllers, however, are still the most commonly used technology to operate home appliances. Remote control with infrared ray has been in use since 1975 in Japan and is a reliable method with less small false detections. Though remote controllers are commonly used today, there are two major problems. The first problem is that users need to use a particular remote controller corresponding to a specific home appliances. For example, when users try to turn on the air conditioner, they need to find and use a remote controller for that air conditioner. They can use the remote controllers for TV instead. Such a number of remote controllers are confusing and take up spaces. Another problem is that remote controllers are easily left behind without being sanitized. According to a report on the COVID-19 health crisis, a large number of viruses were found on the remote controllers in a huge cruise ship case. In contrast, COVID-19 are detected few from the light switch or doorknob because they might be considered as items which need to be sanitized. To solve these problems, we aim to create a new home appliance control device that is easy to manage and users don't need to touch directly. So we propose a gesture-based interface to control a smart home. Our system replaces existing physical controls with a temporal sound commands. An array of sensors has been proposed for recognizing various activities in the home. This system called synthetic sensors includes multiple sensors such as accelerometer, hydrometer, and microphone on its single board design. When you twist the faucet in the kitchen to get water, various information such as the sound with a twisted faucet with the water falling and the humidity raised by this falling water would be detected by these sensors. Activity classification is performed on these sensors' values. In addition, the use of the two synthetic sensors enable more advanced sensing, such as counting how much water flows. A small IoT device called NIOK can be mounted on a surface such as a wall. By knocking the wall around this NIOK for a specific number of times, users can turn on or send messages to linked appliances such as lights, TVs, and air conditioners. This device can be used in noisy environment because it does not rely on a microphone. In our method, we obtain signals from an accelerometer attached on user's wrist to record its vibration. If recorded signals match one of predefined commands for home appliance operation, the system sends a corresponding infrared command to control that specified appliances. We use simple gestures such as knocking on or scratching the table to control home products. This is the processing flow of the proposed system. The user wears the device, perform a specific action to generate vibration, and the system recognizes the action from the sensor information. The device sends transmitting request to a transmitter. Then it transmits infrared rays to home appliances. Home appliances react to that command and get working. For a preliminary experiment, we developed a prototype system that has a sound sensor and a microphone instead of an accelerometer. User gesture for a prototype are recognized not with a vibration gesture by the gesture, but with a sound by that gesture. We collected a number of sound recordings used for the learning gesture classification. These sounds were generated on a wooden desk and recorded with USB microphone at a distance of 3 centimeters from the desk surface. And this is the wave image of clapping 2 times. We recorded 150 sound files for each of the following 6 types: 1 single mouse click, 2 double mouse click, 3 single knock on the desk, 4 double knock on the desk, 5 triple knock on the desk, 6 double claps. Every waveform image shows a characteristic waveform. Although mouse clicks are not used as an operation command at last, we add them as a test to confirm the operation of the system. Because it is difficult to perform deep learning with one-dimensional sound signals, we converted them into 2-dimensional spectrogram images. A spectrogram image is that represents an amplitude, frequency, the time of the sound by performing frequency analysis and using color shading. And this picture, this picture shows, this picture is an example of a spectrogram. The closer the color of each point is to red, the higher the amplitude of the frequency. We converted 150 sounds for each of 6 types into 900 images. We used Python and Jupyter Notebook. The training time was approximately 5 hours, performed on PC with AMD Ryzen 300 900X 32GB main memory, GeForce RTX 2070 Super 8GB. We used 6-layered CNN model. We don't use data enhancement and dropout. The table below shows the parameters used. 30 of 150 spectrogram images for each sound were used as a test data to improve accuracy. We developed a remote controller using Raspberry Pi, a popular system on a chip computer system. We implemented the learning process with infrared ray from other controllers and an IR transmission circuit on this small controller. Our learning process with IR signals is based on the library of IR record and playback by Pigpio. In this experiment, we collected acceleration data using Apple Watch Series 3. We used CM Motion Manager to acquire motion data, which can acquire the motion sensor data in the device published by Apple Inc. When the button displayed in the Apple Watch was tapped, the program acquired motion data, including acceleration data. 5 types of gestures were collected: resting, knocking twice on the desk, knocking 3 times, clapping twice, and knocking with a thumb rhythm. We recorded about 100 times for each gesture. The gesture occurred 3 times in one data. This figure left figure shows a graph of the transition of acceleration for 2 knocks. It can be seen the x-axis and the axis reacts twice. Core ML provided by Apple Inc. is used to train the collected acceleration data. It can perform machine learning on device by simply preparing the specified data, and there is no need to build a learning layer or set up an activation function. It supports various types of learning. In this research, we use activity classification. We used Core ML's activity classification to learn. There are 16 classifications that can be used for the learning: acceleration X, Y, Z, attitude, pitch, roll, yaw, gravity X, Y, Z, quaternion W, X, Y, Z, rotation x, y, z. In this research, we use only acceleration x, y, and z. Because there is no significant difference between using all the classification data and using only 3 accelerations. Table below is a settable parameters of core ML. We set batch size for iteration 5,000, prediction window 130, sample rate 50. We conducted a series of experiments to evaluate recognition results. We made 20 trials for each sound to rate the recognition precision of the proposed method. We checked if the sound produced matches the result of the classification. First, we conducted experiments using Raspberry Pi with a microphone attached to it. The experiment results are shown table below. Sounds of clicking on mouse once and twice are not included because these 2 sounds are too quiet to detect using the microphone. All 4 sounds have poor accuracy. It might be because we used sounds recorded using microphone attached to a desktop computer, not a Raspberry Pi, when we trained the model. Next, we conducted experiments to measure the classification accuracy of the core ML model. This table shows the results of the experiments. Almost all the trials are classified as the knocking on the disk 3 times. In our experiment, we use spectrogram images recorded with a microphone connected to a PC for learning, and those images with Raspberry Pi for the recognition task. The recognition accuracy might be improved if we use spectrogram images recorded Raspberry Pi's microphone for both learning and recognition. We are conducting experiments with our recognition model using sound file with a microphone connected to Raspberry Pi. To replace existing remote controllers with our system, more operation commands are needed, such as turning on or off, turning up or down the volume, switching the channels. We are planning to increase and regulate the gestures to correspond more commands. Alexa is one of the most popular speech recognition interfaces, and a number of appliances have compatibility with it. Our approach could solve some of the disadvantages in speech interface, such as longer voice command and effects by background noises. We are planning to conduct user experiments and questionnaire to measure the quality of our system. First, participants in the experiment sit in a chair and type the instructed text into the computer. While they are typing the text, they are instructed to turn on or off the lights 4 times at random time points. We measure and compare the time between the instruction and actual operation when the participant uses the remote controller or our device. The questionnaire is based on the following items: ease of movement, ease of understanding gesture commands, interested in using in daily life, differences from the remote controllers, and comments. We collect the answers to the question on a 5-point scale from dissatisfied to satisfied. And this is references. Thank you very much. Hello? Can you hear me?
Yes.
Okay.
Yeah, we can hear you. We can hear you. Thank you.
Thank you.
Thank you for your presentation. Does anyone have any questions?